Okay, last week we had a lecture which is basically an introduction to what you are going to learn in this subject. Okay, so we have mentioned what are the causes of the global warming, okay, which is the release of carbon dioxide, methane, and other greenhouse gases to the atmosphere. And these greenhouse gases will absorb the heat and release it to the atmosphere. Okay, so it's like trapping the heat. So the more greenhouse gases we release to the atmosphere, then the heat trapping ability of the atmosphere will be more and more serious, okay, leading to global warming. And we have also learned different international treaties or agreement that target to lower the greenhouse gas emissions, okay, like the Kyoto Protocol and also the Paris Agreement. And so in the last lecture, it's more like a big picture of the current situation in greenhouse gas emissions. And today, we will focus it in the construction industry and talk about the embodied carbon. Okay, so for this lecture, we will first of all take a look at the global energy consumption and then the global carbon emissions, and we will talk about the life cycle assessment and the embodied carbon. So given the advancement of energy-efficient equipment being produced, how has global energy consumption patterns been evolving? So about energy efficiency, so maybe the first thing you can, in your head, maybe LED, okay? So when we say energy efficient, then lighting is all about LED. And yeah, when you go to the supermarket or maybe the electrical appliance shops, you will find many energy efficiency label, not just for lamps, but also for the washing machine, for the dehumidifier, for the air conditioners. Okay, so we have different grades of energy efficiency, and the government also talk about energy efficiency all the time, right? So we have so many research and then case study, okay, to find out what are the ways to save energy. So it means that we should have lower the total energy consumption, right? So is that the case? We will find out very soon. So this is a trend of global primary energy consumption by sources, and is from very early, like 1940, all the way to 2023. So you can see that the increase is very serious, right? We have a high, more and more dramatic increase in the primary energy consumption. So like in 1940, 20,000 terawatt hour, and then current over 180,000 terawatt hour. So much larger than some years ago. Okay, and it's keep increasing and increasing. So there is a certain dip in this around this year. So can you guess what happened around those years? There is a dip of global energy consumption. So is it we all switch off the lighting and save energy? Not really. Okay, it's due to the COVID-19. So it affects the global economy, and then yeah, everybody stay home. We don't go outside, and yeah, probably due to this reason, there is a dip in the global primary energy consumption. So what does it mean by primary energy? So the primary energy in this figure include traditional biomass, for example, the dead plants, or maybe the dead animals, or maybe some crops, okay, some yeah, wood, okay. These are traditional biomass, okay, something organic. And coal, oil, natural gas, nuclear power, hydropower, wind, solar, modern biofuels, and other renewables. So these are primary energy. So primary energy is the energy formed in the nature that has not been subject to any human engineer conversion process. Okay, primary energy is something that is available from the nature, okay, without any human engineered process. Okay, that's the primary energy. Like, okay, deep under the ground, okay, we can dig out the coal and then maybe some oil, natural gas. So these are found from the nature. So unlike electricity, okay, for electricity, we need to burn the fossil fuel so as to generate electricity. So electricity is not primary energy. And also for petroleum, okay, petroleum also not primary energy because petroleum needs to be refined by some industrial process. Okay, so without any interference from human activities, okay, those energy available naturally would be the primary energy. Okay, so we see that the consumption of coal is actually getting more stable. Okay, not much increase because we are switching to natural gas. Okay, so even if we are burning fossil fuel, we are switching from coal to natural gas. Okay, because it will release less air pollutants and others, more efficient. So we are using less coal, and we are also consuming other renewable energy. Okay, like hydropower, wind, solar, modern biofuels. So for solar panel, so do you know which country is the largest market of solar panel in the world? It's China. Okay, China, around 1/3 of the energy produced by PV panel is actually from China. And wind power, okay, the wind power, also China. Okay, China has over 40% of the world capacity of wind power. And Denmark produces 55% of its electricity from wind energy. Okay, so they consume, they make use of the wind energy for turning or for driving the turbines so as to generate electricity. Okay, so more than half. And how about hydropower? Hydropower, so the energy from falling water. So also China. China is the largest producer of hydropower. And in Europe, Norway, so 95% of the electricity in Norway is actually generated from hydropower. Okay, so it means if you're in Norway, then probably the carbon emissions would be quite low because when you consume electricity, actually 95% of the electricity is has very, very low carbon emissions. Okay, so the carbon emissions is really dependent on the fuel mix of the electricity. So in Hong Kong, the fuel mix will include natural gas and oil. Okay, and we also import electricity from Daya Bay, which is a nuclear plant. So when you consume electricity, like you can check your electricity bill. If you are like me, live in the New Territories, then the electricity supplier would be the CLP, China Light and Power. So the electricity will be generated by burning oil, natural gas, and the nuclear power. Okay, and if you are living in the Hong Kong Island or Landmark Island, then the electricity will be provided by the Hong Kong Electric. And the Hong Kong Electric will rely on natural gas and oil and small amount of wind energy. So if you compare these two utility company, the emission factor for CLP would be lower because they import electricity from Daya Bay, which is nuclear plant. And for nuclear plant, the carbon emissions will be lower. So I am buying electricity from CLP. So comparing some of you who live in the Hong Kong island, then it means relatively I should emit less carbon dioxide. Okay? And how about modern biofuels? Modern biofuels would be different from the traditional biomass, although also from something organic. Okay, so for example, the ethanol. We can extract the ethanol from some plants, okay, like corn. Okay, so like in the US, some of the corn field, okay, those corn not for eating, okay, not for supplying food to human or animals, but they are for extracting ethanol, and then these ethanol, like alcohol, okay, very effective for combustions. So they would be for combustions and then generating electricity. And biodiesel, okay, biodiesel would be from the animal fats or cooking oil. Okay, in Hong Kong, I think we have a few biodiesel generator. Okay, one in the zero carbon building. So they will make use of the waste oil from the restaurant and then make use of these waste oil for generating electricity. Okay. So before, so in this, this is the cumulative emission or consumption, and then in this figure, this is the primary energy consumption by different country, and these are yearly consumption. So yeah, for China, because of the urbanization, industrialization, and the blooming of the economy, so you can see that China is consuming a lot more primary energy consumption than before. And for Europe, so rather steady and even dropping. So maybe they have some energy efficient policy, okay, for reducing their energy consumption. And for United States, also a little bit steady. And for India, okay, also increasing. So these are the blooming economy. And in line with that, the primary energy consumption will also be increasing. So in this figure, it is the total energy consumption in the whole country. So maybe it's not a very fair comparison, okay, because in China we have a lot of population, right? So let's take a look at the energy used per person, okay, per person. So China would be here, okay, this is the curve for China, okay, also increasing and increasing. But the absolute value of the energy used per person is actually less than that of South Korea, United States, and Canada. Okay, Canada consumes a lot of energy, but they have smaller population. So the energy used per person is actually very large. Okay? And yeah, for developed country, the energy use is dropping, okay, like Canada, United States. So although still very high value, but the trend is dropping, okay. But for the like China and India, they are rising, okay, because we have better the living standards. Okay, living standards in China is getting better and better, and therefore, yeah, industrialization, urbanization, so we are consuming more and more energy. So global energy consumption is generally a function of three factors. Okay, first of all, number of consumers, like the population. okay, the energy consumption in a country or in a region will first of all depends on the population. Okay, how many users, how many consumers are there? And next would be the demand of services. So how much do we need from the energy? And it is dependent on many factors. For example, the economy, okay, the economic growth. So if the living standards is higher and if our salary is higher, then probably we will also consume more energy. I remember that back then when I was small, okay, just maybe in primary school. So after school in the summer, okay, maybe it's very hot and I want to switch on the air conditioner. And my mother will ask me to check the weather report, to check the temperature. So if it is higher than 30 degrees C, then I am allowed to switch on the air conditioner. But now, so when I go back home, my sons has already switched on the air conditioner for the whole day, for the living room and also for the bedroom. Okay, so it's all about the living standard. Okay, it's different from decades ago. And yeah, industrialization, urbanization. So comparing people living in the villages, okay, we are living in the cities. And yeah, we will be using the electrical lighting instead of daylight. And then we use the air conditioner instead of natural ventilation. And we drive and maybe we take train, and then we go to shopping centers where there are air conditioning instead of going to the park and so on. Okay, so these lifestyle also affect the demand of services. And during COVID, so people stay home, right? So and even now, I still have friends who are home office, so they can stay home and still get their salary. So it's this kind of change of lifestyle also affect the demand of services. So maybe back then, okay, before the COVID, everyone go to office to work. So for the office, they have to pay for the electricity fees, and then people may take train, may drive to work, and all contribute to the energy consumption. But now some of us stay home to work without leaving their home, so it will affect the energy consumption. Okay, and the third factors would be the efficiency of services. Okay, like the efficiency of the lighting, the efficiency of the motor, the efficiency or some control system. Okay, we have some advanced sensor control system that can reduce the energy consumption of different kind of systems. So the global population is predicted to increase by 25% over the next 2 decades, with nearly all this growth occurring in the urban areas of developing countries. So for developing countries, the energy consumption will be getting higher and higher because, yeah, the fact is that their population is getting higher. People's income in developing countries are rising, leading to further demands for energy as their expectation increase. Okay, so higher salary, higher living standard, then it's natural that we spend more energy. History suggests that as we improve energy efficiency, rather than reducing energy consumption, it often goes up. So what does it mean? I can tell you a story. Many years ago, before the invention of fluorescent tube, people rely on the incandescent lamps, just the ordinary light bulb, those manufactured by Edison, right? Okay, by Thomas Edison. So we used to use that kind of ordinary light bulb, but that kind of light bulb is not efficient. Okay, only 20% of the electricity is converted into light, and the rest would be heat. Okay, so back then, when we are using the incandescent lamp, it's not efficient, right? And then by the year, like around 110 years ago, okay, so we have fluorescent tube. Okay, we don't have the LED general lighting yet. Okay, back then we only have the fluorescent tube. And the fluorescent tube are much more efficient than the incandescent. So once we have this new product in the market, so people are very happy, okay? They can save a lot of electricity bill. But at the same time, if they can afford that amount of money, okay, then they will install a lot of fluorescent tube in the ceiling. Okay, so it means that when they are just using the incandescent, okay, maybe a few light bulb and then the environment is not too bright, okay, when they have the fluorescent tube, because they can afford the electricity fees. So there is a trend back then, okay, like 100 years ago, the whole ceiling is covered by fluorescent tube. It's not necessary, okay, it's very bright, not necessary to be that high lighting level, okay, but they can afford the electricity fees because of this energy efficient product. Okay, so it turns out that some companies, okay, they cannot reduce their electricity fees, or maybe they don't need to reduce their electricity fees, and it means that even sometimes when we have the energy efficient product, it is not a must that we can reduce our consumption, okay, because it is dependent on the whether people can afford the money for paying the electricity fees. So here it explains this incident. Okay, so to counter the energy consumption. So as efficiency increase, then the cost of energy also needs to rise, so that the net cost to the consumer of using the product or service remains the same while energy consumption reduces. So here it suggests that if the government wants the citizens to reduce the energy consumption, then when we have more and more energy efficient product in the market, at the same time, the electricity fees should be increased, okay, so that you will reduce the energy consumption. Okay, you want to save the money. Yeah, I used to use the light bulb, okay, 100 watt. Okay, but now I use the LED, 3 watt. So, but the electricity fees is getting higher. Okay, then I should switch off the lighting sometimes. Yeah, so as to not to overuse the lighting, because I want to save the pocket, my money. But is it politically palatable? So it will not be welcomed by the citizens, right? When you want to raise the electricity fees, people will be angry. Yeah, so it may not work. So education, and then, so that's why carbon tax that we have mentioned last week would be a probable solution. Okay, you have to give people some incentive, okay, some advantages for them to save the energy or for them to reduce their emissions. Okay, you cannot just rely on their conscious or sometimes economic incentive would be more effective. Okay, the sources of greenhouse gases due to human activities would be burning of the fossil fuels, or some industrial process also produce the carbon dioxide or other greenhouse gases, just like the production of cement. Okay, so in the construction industry, we use concrete as the building material very, very often, right? And for a concrete building, we use a lot of cement. And cement, in the production of cement, we need some chemical process, okay? Chemical process of burning the limestone, and then in this process, in this chemical process, carbon dioxide will be released. And that's why the cement is responsible for quite a high percentage for the global carbon dioxide emissions. Okay, and land use change. Okay, so due to urbanization, so instead of living in the village, people move to the cities. So we need more land for building houses. So it used to be a forest. Now we chop down the trees and then build the houses. So less plants, then less sink for the carbon dioxide. And it will also lead to the greenhouse gas emissions. And also some wetland. Okay, some wetland will also release carbon dioxide. Livestock and agriculture activities. So maybe you have heard of eating beef is not environmental friendly. Yeah, it's due to their digestive process. Okay, in the digestive process of the cow, carbon dioxide, not carbon dioxide, it's methane. Okay, methane will be released. And methane has very high global warming potential. Okay, so that's why people say, not to eat beef if you want to reduce the emissions. And some agriculture activities, like use of fertilizer. Okay, use of many fertilizer will also, chemical fertilizer, will also lead to the release of nitrous oxide. And nitrous oxide is also greenhouse gases. Okay, waste management, the decompose of organic waste. If it is an anaerobic decomposition of the organic waste, then it will also lead to the release of methane. So in the landfill, okay, sometimes we may capture the methane released in the landfill for generating electricity, okay, because the methane is highly combustible. And refrigeration system. So in the refrigeration system, we use refrigerant, and most of the refrigerant are greenhouse gases. Okay, if these refrigerants leak to the atmosphere, then it will contribute to global warming. So these are the greenhouse gases that we mentioned last time. Carbon dioxide, nitrous oxide, and not to confuse nitrous oxide with nitrogen dioxide. Okay, nitrous oxide is N2O, nitrogen dioxide is NO2, so they are different. So here we mean nitrous oxide, N2O. And methane, SF6, hydrofluorocarbons, perfluorocarbons, so they are commonly used for refrigerations. And then this NF3, okay, these are the common sources of greenhouse gases. And for the radiation effect for all the common greenhouse gases, 74.4% is due to carbon dioxide. And then next, methane, and then nitrous oxide and other something gas. So hydrofluoro or perfluoro, okay, would be here. Okay, so because carbon dioxide is still the predominant greenhouse gases in the atmosphere, so we use the term carbon footprint. The global carbon dioxide emissions is like this. So before the Industrial Revolution is very, very low. Okay, but after that, we are consuming more and more and more. Okay, just in like a little bit more than 150 years, okay, we already, how many times? So it used to be around just zero, but now 35 billion tons of carbon dioxide. So it's quite scary. And in this picture, it shows the annual carbon dioxide emissions in different countries in the year 2022. And the darker the color, the more emissions, okay, would be by that country. Okay, like for China, is the top emitter for carbon dioxide. So as I mentioned earlier, so if we just look into the carbon dioxide emissions, it may not be very fair, okay, because we have a lot of people living in China. Okay, so we will, in some later slides, we have the per capita, per person trend of the carbon emissions. Another factor is that China is the, we call it the world factory or the global factory, right? So many products are actually made in China. And it means that we are making a lot of products here in China and export the products to other countries. Okay, and these products will be consumed in other country, so maybe in the US. So it's like they are transferring those carbon emissions to China, okay, because China is the factory. Okay, we produce a lot of products and therefore high carbon dioxide emissions. But actually these products are not consumed here in China, but elsewhere. Okay, so this factor also affects the carbon dioxide emissions and lead to the high emissions rate in China. And the economy of China is rising and rising in recent years. Okay, but many years ago, the emissions is still low. So if we want to analyze the historic emissions around the world, then we should refer to the cumulative emissions. Okay, so this graph shows the cumulative carbon dioxide emissions from many years ago, okay, like from 1750, okay, almost 200 years ago, okay, it's almost zero. And then for industrial revolution, it happens in Europe, or to be more specific, in the UK. So you can see that UK has the carbon dioxide emissions very early in time because they are the origin of the Industrial Revolution. Okay, but United Kingdom is not a very big country, so the cumulative carbon dioxide emissions is not as high as United States. Okay, so this is the emissions from day one. Okay, in almost 200 years time, United States up to now has emitted this amount of carbon dioxide emissions. Okay, and for China here, so maybe some years later we would be catching up United States, okay, which is not very good. Yeah, so China has, so that's why the many countries are like the United Nations, they are asking China to peak the carbon dioxide emissions in the coming years. So it means they want China to reduce or start to stable their carbon dioxide emissions. Okay, and other countries, Canada, Brazil, India, okay, these are developing countries, so their emissions is also getting higher and higher. And these are annual greenhouse gas emissions. So in the previous graph, it is cumulative. Okay, so from day one all the way to current emissions. And this one is the yearly emissions, annual emissions. So the annual emissions in China is very high. Okay, but this is not per capita, okay, not per person. In the next graph, this is per person. So you can see the trend, okay, it's getting higher, but the absolute value is still less than that of United States and Canada. Okay, but their per capita emissions is dropping, while in China is rising. Okay, this is the global greenhouse gas emissions by sector. Okay, different type of industry. Okay, the largest one should be this one, manufacture and construction. So manufacture of products, any kind of products, and building. Transport, okay, the consumption, due to the consumption of electricity and maybe gas in residential building, in commercial building, okay, and agriculture, change of land use, waste, industrial process, and so on. Okay, so for construction, okay, we are in this sector. So constructing building would be responsible for a lot of greenhouse gas emissions. And inside buildings, we are also responsible for the greenhouse gas emissions. Like in this lecture theater, we are using electricity to support the computer, the lighting, the air conditioning, the projector. And when we go home, I will switch on the air conditioner, okay, and then maybe watch TV, the lighting, and charge my phone, and maybe you will drive home. So but driving is the transport. Okay, but inside the building, there are so many equipments that will consume electricity. And if in your region the electricity is generated by burning the fossil fuels, then it will be responsible for the carbon dioxide emissions. Okay, so buildings use 30 to 40% of the global energy and contribute to around 1/3 of the global carbon dioxide emissions. So in total, okay, in the whole world, the buildings, okay, including the process of construction, the materials consumed in the construction process, the energy consumed in the construction process, and also during the operating stage, consumption by the air conditioning, the lighting, the lift, the escalator, the all kinds of building services system. So it is responsible for 1/3 of the global carbon dioxide emissions. So you can see buildings are so much related with the carbon dioxide and other greenhouse gas emissions, and they are affecting one another. Okay, our building industry affecting the carbon emissions, and the degree of carbon emissions and also the carbon policy will also affect this industry, which will be explained very soon. So reducing energy consumption and reliance on fossil fuel in building sector is therefore crucial to reduce the global greenhouse gas emissions and to mitigate the impact of climate change. Okay. So if you are in the building industry, you should know the EMSD Building Energy Code, right? The Building Energy Code, or the Code of Practice for Energy Efficiency of Building Services Installation. So in this Code of Practice, it will state the minimum efficiency requirement for the lighting installation, electrical installation, air conditioning, and the lift installation. So the government, the Hong Kong government, is promoting energy efficiency in the recent decades, like in the recent 20 years. Yeah, and the EMSD also issue the label, okay, the energy efficiency label, like for the fridge, for the air conditioning, and so on. So all these would be with the objective for reducing the electricity consumption and therefore hopefully reducing the carbon dioxide emissions. So buildings contribute 30% of the world's carbon dioxide emissions. The cost of carbon will impact on running costs, the price of construction materials, and the cost of traveling between buildings. Why is that? So the cost of carbon, one example is the carbon tax. So we don't have the carbon tax here in Hong Kong currently, but you can imagine if in the future, if we need to pay for the carbon tax for all kinds of products that we consume, then building would be much more expensive, electricity would be expensive, okay? And the transportation costs will also be expensive unless we switch to renewable energy for generating electricity, okay? So the carbon pricing will affect the building industry and also how we spend the money, our lifestyle. Building needs to adapt to changing climates in the future, potentially higher temperatures and more extreme weather events. So the rising of greenhouse gas emissions cause global warming and climate change. So I mentioned the EMSD Building Energy Code earlier, right? So it states some design criteria for the air conditioning system. And one of the design criteria is the outdoor air temperature. So it used to be 33 degrees C, but now it is revised to 35 degrees C because of global warming. So the climate change, like global warming, affecting our building design, and the more and more frequent thunderstorm, heavy rain will also affect the building design. Okay, so we need the building or the urban environment to be like a sponge, okay, to absorb the water and to be more resilient to these extreme weathers. So the global warming, climate change is caused by building activities, okay, and at the same time, the climate change is also affecting the building design and others. Energy legislation in building sector. Environmental rating tools. So the building legislation is like what I mentioned, the EMSD Building Energy Code, and the environmental rating tools like the BEAM Plus, and also LEED, L-E-E-D, okay, which is similar green labeling for buildings. Okay, so now we will talk about the life cycle assessment and embodied carbon. Okay, life cycle assessment. So what does it mean by life cycle? Carbon footprint is typically used to indicate the extent of greenhouse gas emissions resulting from a person's or an organization's activities. So like the carbon footprint of a Hong Kong citizens, okay, like around 4.5 tons of carbon dioxide. So this is the carbon footprint for one person. And we may also use the carbon footprint to state the carbon dioxide emissions due to an activities, okay, maybe a BBQ by company, okay, some, yeah, and maybe some like for one building, for one region. So this is the carbon footprint. And carbon footprint assessment is the measurement of greenhouse gas emitting process, their origins, their composition, and amount. So origins would be like we have different greenhouse gas emission sources. Okay, maybe due to the leakage of refrigerant, or maybe due to the consumption of electricity. So these are the origins. And apart from emission source, we may also have the sink for the greenhouse gas, like planting. Okay, planting trees, and trees can absorb the carbon dioxide. So the sources here, or the origins, will include the sources which emit carbon dioxide, and also include the sink for absorbing carbon dioxide. Okay, and the composition, so whether we have carbon dioxide only or also methane and nitrous oxide, and how much are released. So if you want to really do a carbon footprint assessment, like for a building, you need a lot of data. Okay, you need all the sources, all the sink, and then what kind of greenhouse gases will be released, how much of them will be released. So it's a very complicated process. And before we can talk about carbon footprint assessment, we need to learn a concept which is called life cycle assessment. Life cycle assessment, or LCA, is the investigation and evaluation of the environmental impacts of a given product or service caused or necessitated by its existence. So please note that life cycle assessment is about environmental impacts, not just about carbon dioxide emissions or greenhouse gas emissions. So many different kinds of environmental impacts can be studied using life cycle assessment. So maybe, so currently we are not allowed to use plastic straw, right? So when you go to buy a bubble milk tea, so you should be given like a paper straw, but not plastic straw, right? And some of the products in the market, okay, will be like selling some aluminum straw, okay, and they will tell you that it's a very environmentally friendly product, okay, you can use it many times, and for the plastic straw, it will be throw away direct after using once. So how to compare which one is more environmentally friendly? Aluminum straw or plastic straw or paper straw. So it's not just about how many times do you use. Okay, it's also about the material. Okay, what kind of material did you use? Okay, for the aluminum straw, okay, aluminum is a kind of metal. So in order to produce this aluminum straw, you need to extract many raw materials like iron and then other kind of metals, and then go through many processes and consume a lot of water. And in this industrial process, some toxic material may also be produced. And finally, okay, the straw will be transported all the way from the factory to the retail, and then you buy it home. And maybe you use it only for once. How many of you have bought the aluminum tube or other kind of straw? I have bought a glass straw for my son, and he likes bubble milk tea, but he only used it for like less than 10 times. Okay, then it's not environmentally friendly. Okay, because we didn't use it enough. Okay, so remember, for all kind of these environmental products, you have to use it and use it and use it. Okay, otherwise it is only a gimmick to attract you to buy it. So in order to assess more in a systematical way, okay, how to assess whether a product is environmental friendly or not, we use the concept of life cycle. And in a life cycle, it includes a lot of process, all the way from material extraction, and then processing, manufacturing, and then transportation, and the usage process, and all the way to disposal. So how you dispose that product. So this is the whole life cycle. Okay. So if you buy a aluminum straw, okay, if you throw away to the landfill, okay, then it is a waste of material. Okay. But if you recycle the aluminum, then the emissions may be lower. Okay, so every decisions from the material, the transportation, how you use it to disposal, all these will affect the whole life cycle and the emissions. And remember, for life cycle assessment is for many different kind of environmental impacts, and global warming is only one of them. Other may include maybe the ozone depletion, maybe the human toxicity, or it may be the water pollution, air pollution. So all these are environmental impacts. And global warming is usually represented by the carbon dioxide emissions. It's only one of the impact category. Okay? So the life cycle assessment will include all these stages. Okay, raw material extraction, and in this process there will be certain impact. Okay, in every process here there will be some inputs and outputs. The inputs may be consuming of materials, water, or energy. Okay, and when you extract the raw materials, you will also output some waste, maybe polluted air, polluted water, and the emissions of carbon dioxide. So these are outputs. So in every process, there will be certain inputs and outputs, and resulting in different kind of impact to the environment. Okay, material processing, okay, maybe in the factory, okay, and then production, manufacturing, assembly, and then transportation to the retailer, to the warehouse, and we use it, okay, the usage phase, and finally the end of life. So how you treat the final product, how you dispose of the final product, and there will be certain impacts. Okay, so this is the whole life cycle. And we want to close the loop. We have the term called close the loop. Close the loop is to extend the process from end of life to raw material extraction. So it means that when you throw away something, we want to make it to be the material of a new product. Then it is to close the loop. Okay, so in the building industry, we also want to close the loop. So when we tear down a building, okay, when we demolish a building, we want the waste to be the raw material of a new building. Okay, we want the waste to be useful. Okay, then we can close the loop and to reuse and reuse the materials over and over. So LCA, Life Cycle Assessment, provides a comprehensive approach to understanding the environmental impacts of a product. So maybe a water bottle, maybe a straw, maybe a building. The carbon footprint analysis is only a measure of the climate change impact, global warming implications. And LCA is useful for analyzing many different kinds of environmental impacts, not just global warming. LCA provides an important methodological framework for carbon footprint assessment. So it provides a framework for us to compare. Okay, usually the life cycle assessment is for comparison. Okay, like maybe we have two designs for a water bottle, and we carried out the life cycle assessment, and we want to find out which design will have lower environmental impacts. Okay, so LCA is usually for comparison instead of finding the absolute amount of environmental impacts. Because in the life cycle assessment, we need to make a lot of assumptions, and sometimes there are so many uncertainties. Okay, so the absolute answer may not be too meaningful. Okay, but if we make the same assumption and then comparing two different products, then we have a conclusion. You see what I mean? Okay, so there are too many uncertainties in the LCA assessment such that we need to make assumption. But for similar design, similar product, then we make the same assumption, okay, so that we can do the comparison fairly. So as I've mentioned earlier, life cycle assessment can be used to study different kind of environmental impacts. So the environmental impacts include all these, okay, climate change, ozone depletion, human toxicity, and particulate matter, the PM 2.5, so it's about the air pollution, ionizing radiation, photochemical ozone formulation, the ozone, acidification, and then eutrophication, and the land use, ecotoxicity, water resource depletion. So all these are different kind of environmental impacts. And for different stages in the life cycle of a product, like a water bottle, we have different inputs and outputs. And these may lead to climate change, may lead to the release of the PM 2.5 and then polluting the air or affecting the human health, or leading to water resource depletion or resource depletion. Okay, so for any human activities, for a product, we can use the life cycle assessment to study its environmental impact. And under the category climate change, we use carbon dioxide emissions to assess the global warming effects. So people inside buildings use energy. So constructing and refurbishing buildings requires energy. Okay, during the construction process, we consume energy and we consume resources. And these resources also relying on consuming more energy and resources so as to produce that kind of product. Commuting to and from the buildings consume energy, like traveling, okay? And not just about the construction of the building in day one, but also including the refurbishing and renovation. So you can think of maybe you move to a new house. Probably you want to do some refurbishment. Okay, maybe do some painting, and then buy new furniture, new curtains. So these kind of refurbishment, renovation will also consume energy and contribute to the carbon dioxide emissions. So construction, refurbishment, renovation, and travel. So all these are related to buildings. And these three categories also contribute to greenhouse gas emissions. And therefore, we have three kinds of carbon footprint generally. We have operating carbon, embodied carbon, and transport carbon. So three adding together, the total, the overall would be the whole carbon footprint of a building. So first of all, operating carbon. What is the operating carbon? So in the operating stage of a building, we consume energy, consume electricity, and contribute to carbon dioxide emissions. For example, the using of different building services system, the lighting, the air conditioning, and then the pumps, the lift, the motors, the exhaust air fan. So all these will contribute to carbon dioxide emissions. And it happened during the operation phase. So we call it the operating carbon. Okay? So operating carbon is very easy to understand. And it is also easier to assess. Just check the electricity bill. Okay, and for me, I consume electricity and also the town gas. So we check the bill, and you can estimate the operating carbon. Okay. Next is the embodied carbon, which is what we are going to talk about today. The embodied carbon will include the carbon emissions in day one. Okay, for the construction of the building, the usage of all kinds of materials, and then the energy consumed in the construction phase, plus the carbon emissions due to the refurbishment, the renovation, maybe every 10 years, every 5 years. Okay, so these are embodied carbon. So even if no one moves in, okay, no one lives in that building, the building already has the embodied carbon. Okay? And the last one is the transport carbon. And we need to study the transport carbon because if a building is located in the rural area, okay, which is not like here in Tsim Sha Tsui, okay, very densely packed, every building's very close to each other. So it's in this kind of environment, it's very difficult to utilize daylight. Okay, so that I need to have the electrical lighting, I need to have the air conditioning, so I cannot just open the window. Outside the air is so polluted. But in the rural environment, maybe if I construct a building, I can utilize daylight and maybe more natural ventilation, and so as to reduce the operating carbon. Okay, but at the same time, people live in the city center. So if your office is far away, then you have to transport a long way to work. So the transportation will also lead to carbon dioxide emissions. So apart from embodied carbon for building construction, renovation, and then operating carbon, the operation of the building services system, we also need to consider the transport carbon. Okay, in order to make a fair comparison, the whole carbon footprint of the building. Yeah, so operating carbon would be the electricity, gas, and other fuels used in the building for the heating, cooling, ventilation, lighting, hot water, computer servers, or other electrical equipment. And the embodied carbon is the energy or the carbon, okay, emitted in manufacturing, delivering, and installing the materials used to build and refurbish and fit out a building, and also their disposal at the end of life. So embodied carbon is much more complicated. So you have to have a long list of the materials being used in the construction. Okay, how much concrete, and then maybe ceramic tiles, and then glass, aluminum, and then maybe plastic, and maybe some paint and everything. You need to have a long list, and how much they are used, the kg, or the volume, okay, and how much energy is being consumed during the construction phase, and how many times of refurbishment, renovation. And you also need to assume or make some guess in the end of the day, okay, 50 years later, when this building is being demolished, how are you going to treat the waste and the energy consumed for demolishing the building? How you treat the waste. So all these will affect the embodied carbon. And the transport, the energy used or the carbon emissions to get people to and from the building, maybe by vehicle driving or by public transport or maybe bicycle. Okay, so all these affect the carbon. Okay, this picture explains the three kinds of carbon. So operating carbon, embodied carbon, and the transport carbon. So for operating carbon, is mainly about the electricity consumption, the gas consumption, energy consumption during the operating phase. So if it is about electricity consumption, then the fuel mix of carbon emissions will the fuel mix of the electricity generation will highly affect how much carbon will be produced. So whether you are using renewable energy, nuclear power, or burning the fossil fuel will affect very much the operating carbon. Okay, just like what I mentioned earlier. So I am buying electricity from CLP, and CLP import electricity from Daya Bay. So probably their emissions will be lower. Okay, so the fuel mix of the electricity will affect very much the operating carbon. Okay, and there will also be distribution loss. Okay, so every conductor will have resistance. Okay, so it means that along the transmission cable, there will be certain power loss. And these power loss actually should also contribute to the operating carbon. Okay? And for a building, maybe they have the PV panel to offset the operating carbon. And at the same time, maybe the refrigeration or other process may have leakage of some kind of greenhouse gases. Okay, and natural gas. So natural gas may also have leakage, and it is also contributing to the operating carbon. Okay, so maybe you would think, so the leakage or the distribution loss is not happening inside my building, it's outside along the transmission, far away from my building. But you are responsible for that also, because it is due to your consumption of electricity. So they need to transmit the electricity far away from the generating plant so as to supply the electricity to your building. And therefore, there is transmission loss. Okay, so the transmission loss will also count towards the operating carbon of a building. Okay, and for this, we will discuss this boundary later, okay, when we study the carbon footprint assessment in the later lectures. So this is the operating carbon, and for the embodied carbon, so we extract the raw materials, okay, and in this process, we consume electricity, consume energy, and maybe some process will also release the greenhouse gases, okay, consume electricity. And the transportation to the warehouse, transportation to the retail shops, and maybe we import the materials far away from the region, from our building. So all these also lead to the embodied carbon. And the transportation, the transport carbon, so by public transport, by car, or you walk, or by bicycle. So yeah, that's the transport carbon. Maybe we can take a short break. Okay, so after the break, we will continue with the slides. So I hope that we can have time to finish the slides, and we have one tutorial explaining the embodied carbon calculations. Okay, I think we can continue the lecture. So before the break, we have learned different kind of carbon related to a building. Okay, we have the embodied carbon, the operating carbon, and the transport carbon. And for today, we will focus on the embodied carbon. Energy and carbon profiles in building. So for any kind of carbon, the unit would be carbon dioxide equivalent. So if you remember last week in our first lecture, we have already explained the concept of global warming potential. Okay, there are different kinds of greenhouse gases, carbon dioxide, methane, nitrous oxide, and they have different kinds of radiative forcing. So it means their heat trapping abilities are different. Okay, so in order to compare them fairly, we will convert the methane, the weight of the methane, the quantity of methane or nitrous oxide into carbon dioxide equivalent, okay, by using the term global warming potential. Okay, so greenhouse gas emissions are quantified using kilogram or sometimes ton, okay, kilograms or tons of carbon dioxide equivalent, which allows different forms of energy consumption, electrical, heat, embodied and transport to be compared using a single matrix. Okay, so for carbon footprint, we use the unit ton or kg carbon dioxide equivalent. Okay, so that's why you see the E here. The E represents equivalent. So it means it has already incorporated the global warming potential. Every materials or product used in a building has embodied carbon. Okay, unless it's something from the nature. Okay, but if it is man-made product, then it will have certain embodied carbon. Embodied carbon of a building material refers to the greenhouse gas emissions arising from its manufacturing, transportation, storage, installation, maintenance, and disposal at the end of life. So every stage in the life cycle of that product. Okay, for embodied carbon, we use the life cycle concept to do the assessment. So from material extraction, processing, and then manufacturing, transportation to the factory, and then to the warehouse, and installation, maintenance, maybe every 10 years we need maintenance, and finally, when it is not usable, then we dispose it. So how you dispose it, whether you throw it away in the landfill or you recycle. Okay, so all these will affect the embodied carbon. And it involves complex computation in the large supply chain involved in construction, fit-out, maintenance, refurbishment, and eventual demolition of the buildings. So, like I am making something, okay, maybe handcraft. Okay, maybe I am using some fabric, okay, to make a dress, for example, and I want to estimate the carbon footprint of making that dress. But the dress, I just bought the fabric, I just bought it from Century Pole. So how can I get the data? Okay, the data, the embodied carbon of the material, okay, actually depends on the supplier, okay, depends on the manufacturer, and not every product will have the carbon emissions data. So that's why it makes the calculation, the computation of embodied carbon very complicated, and it may have many different uncertainties. Okay, importing goods from overseas may reduce the emissions in purchasing country, but emissions due to manufacture haven't disappeared. Okay, so importing materials from China, okay, and then sent to the US. So locally, the emissions may be reduced, okay, but actually it's just transfer the footprint to elsewhere. Okay, so that's why we should consider the whole life cycle. Okay, so the embodied carbon of that material, no matter where it is manufactured, should be included. Yeah, major developed economies are typically net importers of embodied carbon emissions. So if the product is made in China, so the carbon emissions is actually released in China, but they import the product. So it means they import the carbon emissions also. Okay, so these are different, important concepts. So when we describe the embodied carbon, the boundaries are very important. Okay, the boundaries, it means that in the whole life cycle, so we may estimate the embodied carbon from cradle all the way up to when the product is manufactured and sent to the warehouse, or from cradle to the site, that is, all the way from material extraction, manufacturing, transportation to the warehouse, and then to the construction site, or the whole life cycle, okay, from cradle to grave. So different boundary, and it is necessary, okay, because like if I am the manufacturer of the water bottle, or maybe I am the manufacturer of some furniture, or maybe the manufacturer of some brick, okay, for construction. So if I am the manufacturer, I cannot control the construction process, right? I can control only up to when the brick are sent to the warehouse or some distribution center, okay? But if you are the building designer, you want to compare the building design, okay, to several options, and then you may have different construction design, different approach, and so that it will affect how you utilize the brick, how you the energy consumption during the process. So then the embodied carbon may be up to the construction site, okay, or maybe even cradle to grave, the whole life cycle, okay. So when we do the embodied carbon assessment, we need to set the boundary, and there are several boundaries that we may use: cradle to gate, cradle to site, and cradle to grave. Okay, cradle is 搖籃, okay, so when the baby is born, okay, so from the day that the material is born, okay, is the cradle. So cradle to gate would be the energy or carbon. So dependent whether you are calculating the embodied energy or embodied carbon. So if you are calculating the embodied carbon, then is the carbon from cradle to the factory gate of the final materials or product. And the cradle means the material deposits within or on the ground. So from extracting the materials, okay, from extracting the materials and then manufacturing, the process and the transportation to the warehouse, okay, or to the factory gate. And cradle to site would be the carbon for cradle to gate plus delivery to the installation site, like the building or the construction site, and there should be allowance for site and fabrication wastage. Okay, so maybe there will be construction waste, right? So in the construction site, maybe you need to build a wall, but the material that you order, okay, must be more than enough, okay, and after finishing that wall, then there will be certain construction waste. So you have to allow certain wastage of that material. And the construction activities associated with the installing of the material and product. So for installing that product, maybe the ceiling, okay, maybe the false ceiling, maybe the material is stainless steel, okay, but when you install the material, you may need to consume certain energy, consume certain electricity. So it also contributes to the carbon emissions. And these will be included in cradle to site embodied carbon. Okay, so cradle to site embodied carbon would be the cradle to gate carbon plus the wastage, plus the carbon due to the wastage and the construction activities. And finally, cradle to grave is everything. Okay, everything associated in the life cycle of that product, from cradle to end of life. So like here, we have cradle to grave. So from cradle, we extract the raw materials and then some industrial process, some manufacturing process, transportation to the warehouse, which is the distribution center. So up to here, so from cradle and then up to here, it is cradle to gate. Okay, so if I am the manufacturer, probably I will have the capacity to estimate the cradle to gate embodied carbon, right? And when the product, okay, you buy the product from the warehouse and you use a truck to transport the product to the construction site, and you will order some more, okay, allow some wastage, and in the process you may have to spend, you may have to consume certain electricity. So these processes will also result in carbon emissions. So up to this point, okay, after the construction or after finishing that construction process, utilizing the product, then it is cradle to site embodied carbon. Okay, and the product, okay, like this brick wall, will be in operation. Okay, so during this phase, there should not be any embodied carbon because it's the operation stage, unless this product needs some renovation or refurbishment. Okay, maybe every now and then you may need to renovate the brick wall, to refurbish the brick wall. Then it will also include some embodied carbon, okay, during the operating phase. And at the end of the day, when that product is being thrown away, okay, demolished, then certain carbon will also be emitted. And it depends on the disposal process, whether you throw away into the landfill or recycle the product. So up to this point would be cradle to grave. All right. So 3 different boundaries for the assessment of embodied carbon. So calculating the embodied carbon of initial construction. So initial construction is the construction of that building in day 1. Okay, not about the renovation every 10 years, not about the refurbishment of the interior. Okay. So an embodied carbon assessment is basically a bill of quantities using carbon rates instead of cost rate. So for a building project, we have some bill of quantities, like in the tender process, you have a long table summarizing all the materials to be consumed. And instead of money, so the unit rate instead of money, here we use the carbon emissions as the unit rate. So we have a long list, and then so as to estimate the initial embodied carbon. So all the values of each material or product are added together to give the total for the building. And once again, we will be using the carbon equivalent as the unit, kg or ton of carbon equivalent. So like here, maybe reinforced concrete, metal, and then some other. So you have the weight, and you have the emission factors, maybe certain carbon equivalent per kg. Then you can calculate the embodied carbon of that material. And we add up together to find out the total. Okay, something like this. Of course, this is a simplified table. So this figure summarize the steps for estimating the embodied carbon. So first of all, we need to know the material quantity. So how much tons or kg of material, okay, maybe from the bill of quantities, and then multiply by a factor. So we usually call it the emission factor. So maybe for every 1 kg of concrete, how many kg or ton of carbon dioxide equivalent will be released? So this is the emission factor. So material, maybe by weight, maybe by volume, maybe by quantity, multiplied by the emission factor. Then we have the embodied carbon. Okay? So if this emissions factor is based on the manufacturer data, then probably this is the cradle to gate embodied carbon, right? Up to the warehouse. So this is what the manufacturer can control. And if you add to the cradle to gate embodied carbon, so also the waste, okay, allowing some wastage in the material, and adding the transportation from the warehouse to the construction site, and also the site activities. So adding all these carbon emissions, okay, due to wastage, transportation, site activities, okay, adding these to the cradle to gate embodied carbon, then you have the cradle to site embodied carbon. All right? Okay, breakdown of embodied carbon. So the most important aspect of calculating the embodied carbon is to obtain a breakdown by materials or elements for a particular building. Like here, so maybe most of the embodied carbon, okay, 42% is due to the superstructure, and then 13% the substructure, 15% due to the cladding. So different components of the building are responsible for a certain percentage of carbon footprint. So if you want to reduce the emissions, then you can focus in the component which has the largest percentage. Okay, just like you do an energy audit, okay, maybe every month you pay, or maybe you are the boss of a large company, okay, maybe in IFC, own a floor of office, and then maybe every month you have to pay $20,000 of electricity, and you want to know where does the energy being consumed. Okay, so you may install some energy meter, okay, so as to do an energy audit. So where are these electricity being consumed? So maybe by the air conditioning system, 30%. Then you can focus your investment for energy efficiency in the air conditioning. Okay, something like this. And the embodied carbon depends highly on the manufacturing data. But these data are very difficult to get. So if you don't have the manufacturer data, then we can refer to some standard or some guideline. Like this is the from the assessment report of IPCC. So IPCC is the International Climate Organization by the United Nations, and every several years they will publish some report. So in this report, they have some recommended embodied carbon for different kinds of construction materials, timber, and then concrete, stone, steel, recycled steel, iron, and you can see quite a large variation. Okay, like for metal, steel, or aluminium. So usually if it is a kind of metal, then the embodied carbon will be larger. And for timber, it could be a negative value. The embodied carbon for timber can be negative value. Why is that? Because in order to manufacture timber, you need to grow a tree, right? And during the years of growing of that trees, the tree will absorb carbon dioxide. So it acts like a sink of carbon dioxide. So for the life cycle of the product timber, sometimes some duration of the life cycle, okay, will absorb carbon dioxide, resulting in a negative embodied carbon. This is another example for the embodied carbon from the inventory of carbon and energy developed by the University of Bath. Yeah, just for your reference. And these are cradle to gate. Okay, usually from these kind of code or guidelines, it will give you the cradle to gate embodied carbon, because how you utilize the product will depends on you. It depends on the construction activities on site. Okay, so from the guideline, it is usually cradle to gate embodied carbon. It should be noted that the material or products with the lowest cradle to gate embodied carbon may not necessarily have the lowest greenhouse gas emissions over the life of the building. This is because materials and products have different properties, durability and recyclability. Okay, for example, okay, maybe you want to compare a concrete construction and a steel construction. And steel, okay, a kind of metal. So probably if you refer to the previous table, you will find that the embodied carbon per kg, okay, of steel would be larger than that of concrete. Okay, very probable. But they have different density, right? So if you are building a house with metal or steel structure, probably you will use less, okay, less amount in terms of weight than the concrete. Okay, so you cannot just compare the emission factor. Okay, and also for the steel, when you demolish the building, when you tear down the building, you can maybe reuse the steel or recycle the steel. Okay, so it depends on how you utilize the material and then the disposal, how you treat the waste. And durability, okay, whether some materials are more durable or maybe it need frequent maintenance. So all these will affect the embodied carbon over the whole lifetime of the material. Okay, here is an example, and it involves some calculation. So, yeah, a single skin brick wall, blah, blah, blah. Okay, it's just some explanation. Yep, it's just that we are building a wall. Okay, like this. This is the brick. Okay, this is the brick, and then yeah, we are building the wall like this, simply like this. And here it means a single skin or double skin is because for double skin wall it would be something like okay, very bad drawing. Okay, maybe we are building, we can build a brick wall like this. So you can see that for this brick wall, the thickness will be larger than this. Okay, this one is only a single layer, right? Single layer. So it is, this one has larger thickness. So it is called the double skin wall. Okay, for this one, and this one is the single skin brick wall. Okay, just nothing special. Okay, then the we want to calculate the cradle to site embodied carbon of a single brick thick wall per square meter. Okay, so it's like here we have 1 meter by 1 meter of brick wall. Okay, single brick thickness. Okay, so something like this. And it is given the dimensions of the brick is 215 mm in length and the width 102.5. So if the brick is like this, the length is 215 mm, the width is 102.5, and the height is 65 mm. So this is the UK standard brake. And we have the mass. Okay, the weight of one brake is 2.3 kg. And in order to build a 1 meter by 1 meter brick wall, we need 60. Okay, we need 60 number of bricks. Okay, then we can construct this brick wall. And apart from brick, we also need to use mortar. Okay, so for the mortar, we have the density. Okay, the density of the mortar is given to be 1,400 kg per cubic meter. Okay, and remember, to calculate the cradle to site embodied carbon, we need to include the wastage. Okay, we need to allow some bricks and mortar being wasted. And the wastage factor is 5% for the brick and 10% for the mortar. Apart from the waste, we also need to include the transportation. Okay, the carbon emissions due to transportation from the warehouse to the construction site. Okay, so include the transport. So we have the data for us to calculate the quantity of bricks that we need and the quantities of the mortar that we need. How about the emission factor? So we refer to the next slide. The emission factors for embodied carbon would be 0.55 kg carbon dioxide equivalent for each number of brick. And how many do we need? We need 60 number of brick, right? We need 60 number of brick, but we need to allow 5% of wastage. So we need to multiply 1.05 in order to include the wastage factor. And multiply by 0.55 would be the part of the carbon emissions due to the manufacturing of brick. And for the mortar, the emission factor is 0.156 kg of carbon dioxide equivalent per kg. So we need to calculate the weight of the mortar. And for this wall, okay, we can calculate the volume of the wall. So volume of the wall minus the volume of the bricks will equal to the volume of the mortar. Okay, because the mortar are used in the gap, okay, for sticking the brick to another. Okay, so the total volume of the wall minus the total volume of the 60 number of bricks would be the volume of the mortar being used. Okay, so we have the volume and we have the density. So we can calculate the weight of the mortar and multiply by the wastage factor and the emission factor. Then we have the carbon emissions. And finally, the last factor is due to the transport. And the transport emission factor is 0.15 kg carbon dioxide equivalent per ton km. Per ton km. So it means that for every 1 ton, 1 ton will equal to 1,000 kg. So for every 1,000 kg of goods to be transported, and for every 1 km of distance, transportation distance, the emissions will be 0.15 kg of carbon dioxide equivalent. Okay, and this is only a general value. The emissions will depends on the type of truck, the types of fuel, okay, whether you use diesel oil or biodiesel oil. So all these will affect the emissions factor for transport. Okay. So in order to find out the transport carbon, we need to know the total weight of all the brakes, including the wastage factor and the total amount of motor that we need. And the transportation distance is given, okay, 50 km. Okay, 50 km is the traveling distance. So in the calculations, here we are calculating the area. Okay, the area. So if this is the 1 meter by 1 meter, and we have the brake here. Okay, we have the brake covering 1 meter by 1 meter. So we can calculate the area occupied by the brake. So 1 meter by 1 meter minus the area occupied by the brake would be the area occupied by the motor. Okay, so 1 meter by 1 meter, and the length and the height of one brake, and within 1 meter by 1 meter area, we need 60 number of brakes. So this is the area, and multiplied by the thickness, okay, by the thickness of the wall, then we have the total volume and the density. Okay, so volume multiplied by the density, and we have the weight. Okay, so the total weight to be transported would be the weight of the motor, and including the wastage factor, and the weight of one brake, and we need 60 number, and the wastage factor. So this is the total weight. So 170 kg would be 0.1704 ton. Okay, so very straightforward calculation. And now we can calculate the embodied carbon. So by the brake, we have the emission factors, and we need 60 number of brakes, and the emissions factor is per brake. So 0.55 kg CO2 equivalent per brake. So we only need to multiply by the number of brake, including the wastage factor, okay, and then also the emissions factor, but this time this emission factor is per kg. So we need to calculate the overall weight, okay, which is this, and then multiply by the wastage factor, and we have the carbon emissions, and that by the transport. Okay, this is the emission factor, 0.15 kg carbon dioxide equivalent per ton km. So we need to multiply 0.15 with the total weight, how much ton of goods to be transported, and the total transportation distance. So the total weight is this value. Okay, so we multiply by the total weight, and the distance is given to be 50 km. And adding all these three together would be the embodied carbon, cradle to gate. All right. Okay, so we know that the calculations of embodied carbon for a building involve a lot of data. Okay, a lot of data and some recommendation from the guidelines, some assumption, and according to the book called What Color is Your Building? Measuring and Reducing Energy and Carbon Footprint of Buildings. So which is a like a research study in UK. Okay, so based on this book, the author has collected different initial construction embodied carbon of different buildings, and it is found that the average is around 700 kg carbon dioxide equivalent per square meter, And this area is the inner wall area. Okay, inner wall area. Or it is called the gross floor area, the gross internal floor area. Okay, based on the gross internal floor area. Okay, and it has actually a large variation. So the embodied carbon can range from 300 to 1,600 kg carbon dioxide per square meter of internal gross floor area. All right? And it makes sense. There must be a large variation. So depending on the material you use, whether you use timber or concrete or steel structure, and then the interior refurbishment, and then the construction process. So all these will affect the initial construction embodied carbon. While the structure of a typical building may last 60 or 50 or 60 years, many components in a building, such as the mechanical and electrical plant and the interior furnishing, will be replaced or refurbished, often more than once within the time frame. So within the 60 years, maybe every 20 years we need to replace the air conditioning plant, or maybe refurbish the carpet every 5 years. So refurbishment and fitting out have to be done when a new tenancy starts. So especially for commercial building, like for an office or maybe for retail shops in the shopping center. Okay, every tenancy, okay, will be renewed. So if we have a new tenant moved in, then probably they will do the refurbishment, the renovation, by then. So the whole life embodied carbon of a building includes the initial embodied carbon and also the embodied carbon due to the refurbishment, the fitting out, as well as the end-of-life embodied carbon. So when you demolish the building, how you treat the waste, dispose in the landfill or recycle. Okay? So the whole embodied carbon of the building include, first of all, the initial embodied carbon. So when you construct the building, how much carbon is being released. And then adding the refurbishment and the fit-out carbon. Okay, because every few years you may need to refurbish the building. And finally, adding the end-of-life embodied carbon. Okay, adding these three together would be the overall embodied carbon. And then the overall embodied carbon, adding the operating carbon and the transport carbon, would be the whole carbon footprint. Okay, but for the operating and transport carbon will be discussed not today, okay, next week. Embodied carbon due to tenant fit out. So based on the same book, what color is your building? So based on the same reference book, the carbon due to the fit out would be between 100 to 200 kg carbon dioxide equivalent for every square meter of gross floor internal area. So if we make the assumption that the fitting out will happen every 10 years, then it could represent a significant portion of the whole life embodied carbon of a typical office building. So remember, according to the same book, the average of initial embodied carbon is around 700. Okay, 700 for the initial embodied carbon. And for the fit out, 100 to 200 every time. And in the whole life cycle, which may last for 50 or 60 years, maybe we already need to do maybe 5 times of fitting out at least. Okay, then it will be up to maybe more than that of the initial carbon. Okay, end of life embodied carbon. So what happens to the materials at the end of life is a complex issue because the building is still there. I don't know what would happen 10 years, 20 years later. So various studies based on current demolition practices suggest that site activities and waste transportation and disposal account for between 3% to 5% of the total embodied carbon. Okay, this is only based on the past project, okay, based on some previous projects of demolishing the building. So it will be around 3% to 5% of the total embodied carbon. So this table, lists out different kind of embodied carbon. So first of all is the initial embodied carbon. And then next, in the usage phase, okay, you have the refurbishment, the fitting out, and these are the fit out and refurbish embodied carbon. And at the end of the lifetime of the building, you have to demolish the building, spend some energy, transportation of the waste, maybe to the landfill, or maybe for recycling. So these are the end of life embodied carbon. So adding up together, you have the total embodied carbon. So let's try to compare these two. So which building has lower whole life embodied carbon? Steel structure building or timber structure building? Maybe from our intuition, okay, from our first guess, maybe, of course, timber structure, they have negative embodied carbon, right? Then it makes sense that the timber structure building should have a lower whole life embodied carbon, right? But we also need to consider some other factors like the durability. Okay, so for a steel structure, probably it is more durable, need lower maintenance, so lower the maintenance carbon. And for the steel structure, when it is disposed in the end of the lifetime, okay, they can be reused or recycled. And for a timber structure, yes, it is true that the timber may have a very low embodied carbon. Okay, but how about the construction process? Okay, maybe we have to consume more energy, more electricity for the construction process, and the timber may not be as durable as the steel structure. And at the end of the day, when we throw away the timber, so how will you treat the timber? So if you throw the timber to the landfill and when it decomposes, then the carbon dioxide will be released. Okay? Or you can also capture the gas released from the timber and maybe for generating the electricity plant. So all these decisions will affect the whole life embodied carbon. So you cannot simply compare these two without further information. Okay? This is also referring to the same book, and it gives some typical embodied carbon value for low carbon design, high carbon design, and the average. So in average, the new building, like the initial embodied carbon, will be around 700 kg carbon dioxide equivalent per square meter of gross floor internal area. And for the fitting out, maybe every time 200 kg of carbon dioxide equivalent. And you may need some more refurbishment, minor or major, and maybe some other recladding and the demolition. So these are just some typical figure for your reference. Okay, and lastly, this is based on a research paper that I found for the embodied carbon assessment of high-rise public residential building in Hong Kong. And this is the layout plan. Okay, the typical high-rise public rental housing block in Hong Kong. And it is based on prefabrication construction process. And the gross floor area is like this. So based on the research project, they calculate the cradle to site embodied carbon, and it includes the embodied carbon for manufacturing, processing the material, delivering the material, maybe from manufacturing or prefabrication factory, and then delivering the material of the precast element to the construction site, and the energy consumption of on-site equipment. So that's the energy consumption of some construction process. And lastly, throw away the waste, okay, throw away the construction waste to the landfill. So all these adding up, they have calculated the cradle to site embodied carbon. These are just some equations. So it is just the quantity multiplied by the emission factor, okay, like what we have done in the previous example of the brick wall. And the equation for transport, the embodied carbon due to the transportation would be also similar to what we have done. Okay, the emission factor and then multiply by the weight of the goods to be transported and the total transportation distance and the energy consumption. So we consume diesel oil or maybe consume electricity. Then the carbon emissions will be the total energy consumption, maybe in kilojoule or megajoule, okay, and then multiply by the emission factors. So these are the basic equations for calculating the carbon emissions. So actually, no matter, or for the operating carbon, we have the same equation. Okay, this equation can also be used to calculate the operating carbon. It's just that this energy consumption would be not the construction process, but the operating process. Okay, so when the building is in operation, we consume energy for supporting the lighting, the air conditioning, and others. Okay, so just some fundamental equations. And the result, the concrete, okay, on-site concrete, manufacturing and the construction, and the precast concrete, the steel, so they already constitute most of the embodied carbon. And next would be the timber, okay, maybe for the cladding of the reinforced concrete, and then plaster, and so on. Okay, and you can also analyze the embodied carbon based on different components of the building, okay, like for the staircase, for the internal partitions, the floor slab, or others. And the breakdown would be something like this. So for this residential building, the cradle to end of construction, so this is actually cradle to site embodied carbon. Okay, so for this example, the cradle to site embodied carbon is around 561 kg of carbon dioxide per square meter. Okay, so just some more example for your reference. So we have some examples from the book, which is for the UK buildings, and this is another example for buildings in Hong Kong. Okay, so lastly, I would like to discuss with you the tutorial. So I will finish it very quickly. Okay, this is something similar to the example that we have studied earlier. Okay, with the aid of the data provided in the table below, estimate how much initial and recurring embodied carbon per square meter of the following two types of internal partitions. So per square meter of internal partitions, with their cross-section being shown in the figure. So we have two kinds of internal partitions. Either you use gypsum drywall, or we use the brick wall with plaster coating. Okay, and the cross-section, okay, the composition of the walls are explained in the figure. Okay. Option 1, the gypsum dry walls with a life expectancy of 10 years. So this is a cheap drywall, and it will probably last for 10 years only. So it means if you choose this kind of partition wall, you have to renew or renovate, replace the drywall every 10 years. And for option 2, which are brick walls with plaster coating, and the life expectancy is 50 years, okay, much longer time. Given the office building has a design lifespan of 40 years, okay, the lifetime that in our estimation, okay, we assume the lifetime of the building is 40 years. So it means if you are using the drywall, then you have to replace the drywall 4 times. If you are using the brick wall, you don't need to replace any, okay, because the lifetime is longer than that of the building. So after calculating the embodied carbon, you have to determine which option will you recommend. Any other factors you need to take into consideration when making your final decision. Outline all the major assumptions that you have made in your estimation. So in order to calculate the embodied carbon, we need the emission factors. And the emissions factors are listed here. For bricks and blocks, okay, for the bricks, the emission factor is 0.24 kg carbon dioxide equivalent per kg, okay, per kg of bricks and blocks. And you are also given the density. So if you can calculate the volume, then you can find out the weight. And the weight multiplied by the wastage factor, and also the equivalent carbon, the emission factor, then you have the carbon emissions. And for the gypsum board, okay, also per kg, and you have the density and the plaster, render, and screed. So plaster and render on the brick wall, you have the emission factor, density, and the wooden studs, which is here, like the structure for installing the dry walls. You are given not really the density, okay, something like the density. So 32 kg of these wooden studs inside the gypsum board per every square meter of wall area. Okay, this is the wall area. Okay, and the paint on the 2 sides of this brick wall, you also need to apply the paint. And the paint emission factors, okay, per square meter of the wall. Okay, so these are all we have, and we can calculate the carbon. So first of all, let's calculate the embodied carbon of the gypsum dry wall. So the gypsum dry wall consists of the gypsum board and the wooden stud. So for the gypsum board, we need to calculate the weight and then multiply by the wastage factor and the emission factor. So for the weight, volume multiplied by the density. So for the gypsum board, the thickness is 10 mm or 0.01 meter. And we need 2 of them. And multiply by, let's say, 1 square meter. So let's say we are calculating a wall area of 1 square meter. So if we have the thickness, and if we multiply with the wall area, then we have the volume, right? Area multiplied by the thickness, then we have the volume. Okay, and volume multiplied by the density, density, then we have the weight. Okay, so here area multiplied by the thickness, and we have 2 gypsum board inside and on the 2 sides. Okay, and the density, and we have certain wastage factor, and finally the emission factor. Okay, so we have the amount of carbon emissions, and in between the 2 dry walls, in between the gypsum board, we have the wooden stud, the structure. And the emissions factor is based on weight. Okay, and the density is based on the area. So for every square meter of wall, we need 32 kg of the structure. So this time we don't need to calculate the volume because we already have the weight per 1 square meter. And still we need to multiply by the wastage factor, which is given on this side of the table. Okay, so the weight multiplied by the wastage factor, the emission factor, and we have the carbon emissions per square meter of the drywall, okay, per square meter. And we add them up together, okay, for the gypsum board and the structure, and we need to multiply by 4. Why? Because we are calculating the embodied carbon over 40 years, and the lifetime of the gypsum board is only 10 years. So it means that we need to replace the drywall 4 times. So we multiply by 4. Okay. And next is the embodied carbon of the brick wall with the plaster coating, and once again we are calculating the embodied carbon for every 1 square meter of wall area. So first of all, calculate the brick and blocks. So for the brick and blocks, we have the thickness 100 mm, that is 0.1 meter. So thickness multiplied by the area, we have the volume, and the volume multiply the density, we have the weight. So area multiplied by thickness, and then multiplied by the density, so it would be the total weight. And we need to include the wastage factor of 3%, and next multiply by the emission factor, which is 0.24, okay, per kg. So we have the carbon emissions for every 1 square meter of wall area. And next would be the plaster and the render, and we have 2 layers on the 2 sides of the wall. The thickness is 10 mm or 0.01 meter, and we have 2 numbers, so multiply by 2 and multiply by the area, so we have the total volume, and the total volume multiplied by the density, we have the total weight, so just something similar. Okay, so the thickness multiply 2 number, and the area, we have the total volume, and multiply by the density, the wastage factor, and the emissions factor. So we have the carbon emissions due to the plaster, render, and screed for every square meter of wall area. And lastly would be the paint. So for the paint, the emission factor is kg carbon dioxide equivalent per square meter. So for every 1 square meter of area, this would be the emissions. And we need to apply the paint on the 2 sides of the walls. So we multiply 2, okay, and we apply the wastage factor once again, and the emission factor, and we have the embodied carbon for the paint for every 1 square meter of the wall. Okay, so for the total embodied carbon of brick walls with plaster coating, so we add up these 3, and we only need to multiply 1 because the lifetime of the brick wall is longer than 40 years, and it means that we don't need to do any renovation or maintenance, we don't need to do any replacement for the brick wall. So this is the total. So comparing these two, 40 something and 100 something. So the brick wall will have lower embodied carbon. So probably we will recommend option 2. Okay, so that's the calculation of the embodied carbon. Not difficult at all, very straightforward. You only need to calculate the volume and then the weight and multiply by the wastage factor and the emissions factor. And you have the embodied carbon. Okay, so I think I will just stop here. And next week, we will study the operating carbon and also the transport carbon. Okay, so see you next week.